In this video lecture, I will discuss the mass fragmentation pattern of hydrocarbons. This includes the fragmentation of all types of aliphatic hydrocarbons, cyclic hydrocarbons, and aromatic hydrocarbons. Let us first discuss the fragmentation of alkanes. You know, alkanes usually give a low intensity molecular ion peak. The prominent fragments obtained for normal alkanes are with M by E value 43. Most often, this will be the base peak in the long chain alkane, as it is the more stable cation formed. The propyl carbocation, that is with M by E 43, rearranges to form isopropyl carbocation, which is a stable carbocation, more stable carbocation. And 57, M by E value 57, due to the formation of propyl carbocation. Butyl carbocation, which rearranges into isobutyl carbocation, which is also more stable. The mass spectra of alkanes are characterized by groups of peaks separated by 14, that is of CH2 groups, 14 mass units. Okay, here in this case, the fragmentation of normal pentane, you can see the base peak is formed from this molecular ion with M by E value 72 is propyl carbocation of propyl carbocation, that is with M by E 43. That is the base peak, which rearranges to form isopropyl carbocation. Another possibility for the fragmentation is from here. A propyl radical is eliminated, forming ethyl carbocation with M by E value 29. Okay, then we will have another carbocation formed by fragmentation here. Methyl radical is eliminated, methyl radical is removed to form butyl carbocation, which rearranges to form isobutyl or a secondary carbocation with M by E value 57. Though it is more stable, the fragmented radical is very less stable methyl radical, and hence even though it is more stable, the peak is with very low intensity. The peak formed is very low intensity peak. Okay, another chance for fragmentation is propyl radical. Propyl radical is eliminated, fragmented here. Propyl radical is eliminated to form methyl carbocation. But you know, methyl carbocation is very unstable, and hence its peak also with very low intensity. Okay, in the case of branched alkanes, fragmentation usually takes place at the branching point. For example, in this case, it is 2-methyl pentane. Its molecular ion is with molecular mass M by E 86. When it is fragmented, the fragmentation takes place mainly at the branching point. For example, first it will be fragmented at this point to form an isopropyl carbocation, which is obtained as a base peak, as in the previous case. Then another possibility is fragmentation, or the molecular ion is fragmented at this point, forming this carbocation. It is a secondary carbocation with M by E value 71. There is another possibility for removing a hydrogen radical here from here, forming this tertiary carbocation, and hence the peak of this tertiary carbocation usually with high intensity, because tertiary carbocation is more stable. It is formed by the removal of a hydrogen free radical from this molecular ion. Then another possibility is the fragmentation at this point. An ethyl free radical is eliminated to form this carbocation with M by E value 57. It is the normal mode of fragmentation of 2-methyl pentane. Okay, this is an example of branched alkane. If we take the case of cyclic alkane, you can see the molecular ion peak is somewhat with a high intensity because the cyclic alkanes is reluctant to fragment, because in order to fragmentation takes place, it has to be broken at the, or it has its two bonds should be broken. Two bonds are to be broken in order to fragment. For example, if you take the case of cyclohexane, cyclohexane is fragmented like this. You can see, first of all, a bond is broken here, and then from here two bonds are to be broken. Two bonds are to be broken. So it is highly resistant for the fragmentation. So you can see the molecular ion peak is highly indensed, or we will get high indensed molecular ion peak. After fragmentation, we will get a radical cation. This radical cation with M by E value 56, with an elimination of, or with a removal of an ethylene molecule or ethene molecule. An ethene molecule, or neutral ethene molecule, is eliminated from this molecular ion to form a radical cation with M by E value 56. That is the fragmentation pattern of cyclohexane. Okay, now let us discuss alkene, the fragmentation of alkene. The molecular ion peak, in this case, it is 1 pentene, is obtained at M by E value 70. That is the molecular mass of 1 pentene. Usually alkene fragmented to obtain, or fragmented by the beta cleavage. It is alpha position, it is the beta position. Beta cleavage is the main fragmentation pattern. Thereby, we will get, in this case, a ethyl radical is eliminated to form this carbocation. This is very important. Usually this peak with the 41, M by E 41, is obtained as a base peak. It is allylic cation, or by the beta cleavage of one alkene, we will get an allylic carbocation, which is usually obtained as a base peak. Okay, if we have an alkene molecule with gamma hydrogen, it is alpha carbon, it is beta carbon, it is gamma carbon, whereby there is a gamma hydrogen. Then this gamma hydrogen is abstracted by the unsaturated carbon atom, and bond rearrangement takes place to form a radical cation, and a neutral alkene molecule, usually ethene. Here, gamma hydrogen abstraction followed by the cleavage of beta bond to form a neutral molecule ethene and a radical cation. This rearrangement is usually referred to as McLafferty rearrangement, and this radical cation is referred to as McLafferty rearrangement ion, MR ion, McLafferty rearrangement ion, with in this case with M by E 42. It is one of the important peak, or highly intense peak, obtained from alkene, McLafferty rearranged ion. That is one of the important or prominent peak obtained in the fragmentation of alkene. And so the prominent peaks during the fragmentation of alkene obtained are one at M by E value 41, that is due to the beta cleavage, that is allylic carbocation, and another important cleavage is gamma hydrogen abstraction with the beta cleavage, that is actually McLafferty rearrangement. A gamma hydrogen is abstracted by unsaturated carbon atom, and bond rearrangement takes place in such a way that is a beta cleavage is taking place to form a neutral molecule, usually alkene, and along with the radical cation, which is McLafferty rearrangement ion. Okay, in this case 1 pentene, we will get the McLafferty rearranged ion with M by E value 42 and the neutral molecule ethylene. Cycloalkanes usually give a more intense molecular ion peak. For example, in this case, of cyclohexene, we will get a more intense molecular ion peak at M by E value 82. The prominent fragmentation pattern is retro-Diels-Alder reaction, the fragment obtained by a retro-Diels-Alder reaction, whereby we will get a molecular, the radical cation with M by E value 54. Usually it obtained as a base peak, or it is a more intense peak along with a neutral molecule alkene. The retro-Diels-Alder, by the retro-Diels-Alder reaction, we will get the ethylene radical cation also along with the neutral molecule butadiene. It is the more prominent fragmentation pattern in the case of cyclic alkene. Okay, alkynes usually gives a more intense molecular ion peak, and it fragment as the case of alkene. The main fragmentation is the beta cleavage, whereby a propargyl cation, beta cleavage takes place here with the elimination of ethyl radical. For example, we will get propargyl cation. It is with M by E value 39. A more intense peak with the formation of propargyl cation by the beta cleavage is taking place prominently in alkyne. If a methyl radical is removed, then we will get this cation with M by E value 53. Okay. Then there is a possibility for McLafferty rearrangement as in the case of alkene, whereby a gamma hydrogen is subtracted by this unsaturated carbon atom along with the bond shifting with beta cleavage, forming a neutral molecule ethene in this case, along with the McLafferty rearranged ion, MR ion. Here, McLafferty rearrangement takes place to form a molecular, the cation, radical cation or McLafferty rearranged ion with M by E value 40. The neutral molecule is ethylene as in the case of alkene. Okay, it is the main fragmentation pattern of alkene molecules. Now let us consider the fragmentation in aromatic hydrocarbon. First take benzene. Benzene gives a molecular ion peak at 78, and this remove a hydrogen radical to form phenyl carbocation with M by E value 77. But this peak is with very low intensity because it is the carbocation, the phenyl carbocation is very less stable. Phenyl carbocation is very less stable, and hence its peak is with a very low intensity. It eliminates a neutral molecule acetylene, forming this carbocation, that is cyclobutadienyl carbocation with M by E value 51. That is one of the important fragmentation of benzene. Benzene first remove a hydrogen radical, forming a phenyl carbocation which is very unstable, and hence its peak is with very low intensity at M by E value 77. It eliminates a molecule of acetylene, forming carbocation cyclopentadienyl carbocation with M by E value 51. Okay. Another possibility is elimination of C3H2 from this phenyl carbocation, forming cyclopropynyl carbocation with M by E value 39. A peak at 39 is obtained because of the formation of cyclopropynyl carbocation. So benzene gives these two peaks. The peaks at 51 because of the formation of cyclobutadienyl cation, and peak at 39 because of the formation of cyclopropynyl carbocation. Okay. In the case of substituted benzene, the main fragmentation is at the benzylic position. It is the benzylic position. In this case, an ethyl radical is eliminated to form benzyl carbocation with M by E value 91. It is the most prominent fragmentation in substituted benzene. the formation of benzyl carbocation. Another important fragmentation is removal of hydrogen, one of hydrogen radical at this position, benzyl position, to form this carbocation, this secondary carbocation with the M by E value 119. There are so many possibilities for the formation of different peaks. For example, this benzyl carbocation usually rearranges to form a more stable tropylium carbocation. And so this tropylium carbocation is the prominent peak in the case of substituted benzene. Substituted benzene gives a more prominent peak due to the formation of tropylium carbocation at 91, M by E 91. Another possibility is the tropylium cation removes a molecule of acetylene, forming cyclopentadienyl carbocation with M by E value 65. And so we will get another prominent peak at M by E value 65. There is another chance for removal of or the cleavage at this position, forming a phenyl carbocation with M by E value 77, but it is highly unstable. Remove a molecule of acetylene, forming cyclobutadienyl carbocation with M by E value 51. Then another possibility, the phenyl carbocation remove a molecule of C3H2, forming cyclopropenyl carbocation with M by E value 39. Okay. Another important possibility for substituted benzene is McLafferty rearrangement. Here, the gamma hydrogen atom with respect to this unsaturated carbon-carbon double bond, this carbon-carbon double bond, it is alpha, beta, gamma. So here is a gamma hydrogen atom. It is abstracted by this unsaturated carbon atom along with the beta cleavage, forming a neutral molecule ethene along with the McLafferty rearrangement ion, the radical cation with the M by E value 92. It is another prominent peak in the case of substituted benzene. Substituted benzene gives this much peaks by the fragmentation. The important peaks are one peak at the M by E value 91 because of the formation of a more stable tropylium carbocation. Often it will be the base peak in the case of fragmentation of substituted benzene. Then this tropylium cation eliminates a molecule of acetylene to form cyclopentadienyl carbocation, thereby another prominent peak at 65. There is a chance for formation of phenyl carbocation with very low intensity with M by E value 77 because it is highly unstable. It eliminates a molecule of acetylene to form cyclobutadienyl carbocation with M by E value 51. Phenyl carbocation may eliminate a molecule of C3H2 forming cyclopropenyl carbocation with M by E value 39. One of the important probability is for the McLafferty rearrangement. By McLafferty rearrangement, the hydrogen abstraction takes place at the gamma carbon atom from the gamma carbon atom with the bond shifting or bond breaking at the beta carbon atom or beta cleavage takes place. By the elimination of an alkene, we get a prominent peak. McLafferty rearrangement for the McLafferty rearrangement ion is obtained. In this case, that is propyl benzene. The McLafferty rearrangement ion gives a peak at M by E value 92. These are the important fragmentation pattern of hydrocarbons. I have already discussed aliphatic hydrocarbons, in which alkanes, alkenes and alkanes are taken as examples. I have already discussed cycloalkanes and aromatic hydrocarbons, including substituted aromatic hydrocarbon, substituted benzene. I conclude this video here. Thank you.